Hi all. In the last class we have seen how to construct this forward difference table. In any forward difference table, the first entry is y naught and delta y naught, delta square y naught and delta cube y naught are called the leading differences. Now we will see some properties of these finite differences. The properties are, the first one is delta c is always 0. That means if f of x equal to c for every x, then the corresponding delta of c is equal to 0. So this is just because f of x we define this is equal to c, then you write delta f of x. This is by the definition this is f of x plus h, where h is the interval of differencing, minus f of x. Then this will be always c minus z is equal to 0, whatever be this f of this x plus h and x. So for any constant we have delta, the difference is always, forward difference is always 0. And the second property is delta of c times f of x. This is exactly equal to c times delta f of x. Okay, so you can prove this by starting with this delta c times f of x equal to, by definition this is f of x plus h minus c times f of x, and this is equal to c times f of x plus h minus f of x, and this is nothing but c times, this is our delta f of x. So this proves the second property. And we have the third property is this can be extended to two functions. That is, if we have delta of a times f of x plus b times g of x, then this will be a times delta f of x plus b times delta g of x. This is because if we start with LHS, then LHS can be written as this is a plus a f of x plus h plus b g of x plus h. So this is the step forward with h, then minus of a f of x plus b g of x. So when you rearrange these terms, you can get this is a times f of x plus h minus f of x, and plus b times, if you take b out from this bg x plus h and bg of x, then that will be a g of x plus h minus g of x, and this will give a times delta f of x plus b times delta g of x. So this proves third property. Finally, the fourth property is the nth difference of an nth degree polynomial is a constant, say a coefficient of x raised to n in that polynomial, times n factorial times this h raised to n. This h is the in interval of differencing. So we can prove this by induction on n. So if n is equal to 1, we need to consider the first degree polynomial, first difference of a first degree polynomial. So we assume f of x as a first degree polynomial, say ax plus b. This is the first degree polynomial. Then f of x plus h, in order to consider the first difference, we need to get the f of x plus h. So that is a times x plus h plus b, and if we take the first difference f of x, that is equal to a times x plus h plus b minus ax minus b, so minus of this quantity. So this will be, we can cancel this ax anyway, and the remaining will be a times x, and we have a times x into a times h, and x can be cancelled, so remaining will be ah here, and b can also be cancelled, so we have this is our ah, and we interpret this ah as a as the coefficient of that x, that is x raised to 1. So coefficient of x raised to 1 times, that is nothing but a, and n factorial is 1 factorial here because n is 1, and h is equal to is nothing but h raised to 1. So this proves the result for n is equal to 1. Now we use the induction on this n. If we assume that the result is true for n of every n or every integer less than n, so we assume this is true for n minus 1. Assume result is true for n minus 1. What is the result here? That means if we call this statement as our p of n, then what is p n minus 1? What is the statement corresponding to n minus 1? So that is the statement nothing but the n minus 1, the difference of an n minus 1 degree polynomial is a constant with this x raised to n minus 1, n minus 1 factorial, h raised to n minus 1. So we write the nth n minus 1, not nth, n minus 1 difference of an n minus 1 degree polynomial is, we write that as coefficient of x raised to n minus 1, n minus 1 factorial, h raised to n minus 1. So this is our assumption. So this is the induction hypothesis. Now we prove this result is true for p of n. For that we assume f of x equal to a polynomial a n x raised to n plus a n minus 1 x raised to n minus 1 plus etc etc a naught. So this is an arbitrary polynomial of degree n. We need to prove that this is true for this polynomial as well. So we consider the difference. In order to consider the difference, we write x of x plus h here. So this is nothing but a n x plus h raised to n plus a n minus 1 x plus h raised to n minus 1 plus etc etc a naught. The last term will be the same. Now we consider the forward difference. We need to consider the nth difference. So we evaluate delta n of this f of x. So in order to consider this nth forward difference, so this is going to be delta of delta n minus 1 of delta f of x. This is the definition of delta n f of x, and this delta f of x is f of x plus h. We write this is delta n minus 1 of f of x plus h minus f of x. So from these two equations you can evaluate this difference, f of x plus h minus f of x. So that is going to be the difference between these two. Okay, so once you find the difference, once you try to find the difference between these two, the first term will be a n times x plus h raised to n minus x raised to n. So that will be the first term, and considering all these differences, the last term can be cancelled. Okay, a naught minus a naught, that will be 0, and the second last term will be a1 times x plus h minus x. So this will be the last term of this difference, because this a naught can be cancelled. So this is going to be coming here. So that is equal to delta n minus 1 times of this polynomial. So this is in fact a polynomial of degree n minus 1. Okay, because when you evaluate one particular term of this polynomial, say leading term x plus h raised to n minus x raised to n. Okay, so this is nothing but a raised to n minus b raised to n. So that will be a minus b. A minus b is x plus h minus x times, we can refer that identity, a raised to n minus b raised to n in general, that is equal to a minus b times a raised to n minus 1 plus a raised to n minus 2 times b plus etc a raised to a times b raised to n minus 2 plus b raised to n minus 1. So this is the formula for a raised to n minus b raised to n. We use this formula here. We can get the first term as h, that is because that is x plus h minus x. So that is h here, and the remaining term will be once you consider these terms, we have instead of a we have x plus h, and b we have x. Okay, so we can write it as x plus h whole raised to n minus 1 times, sorry, plus x plus h times n minus 2 times x plus etc. The last term will be x raised to n minus 1. Okay, so that's why we call this is a polynomial of degree n minus 1. Okay, so we write this as this is n delta n minus 1 of h times this polynomial. Okay, we know that this is a polynomial of degree n minus 1. So that is x plus h whole raised to n minus 1 plus etc etc plus x raised to n minus 1. So this is the polynomial. This is the first term of this. When you consider this is h times this polynomial, and x plus h raised to n minus x raised to n is equal to this, means this times n is there, and delta n minus 1 of this, this is the first term of this expression, so plus etc. Okay, this will be the polynomial corresponding to f of x plus h minus f of x. So this is the first term of this one. Okay, when you all the other terms do not contain that x raised to n minus 1 term. So this is the leading term of the leading entry of this polynomial. So we write this as because this is delta of n minus 1, we can use the induction hypothesis. Therefore we need to consider only the leading term of this polynomial. So once you consider this, then delta n minus 1 of we write it as an times h times, when you consider this is the only terms containing x raised to n minus 1. When you consider all these terms, we have n terms here. If you consider this from x raised to 0 to x raised to n minus 1, so we have n terms here. So if we consider the first term, then there will be x raised to n plus n minus 1, and each of these terms, if we consider this x plus h whole raised to n minus 1, x plus h whole raised to n minus 2 times x, and all these terms containing x raised to n minus 1. Okay, when you expand this bracket and multiply it with x, then the leading term will be x raised to n minus 1. So the leading term of all these brackets will be x raised to n minus 1. We have n such terms. So this starts from n times x raised to n minus 1 plus etc etc. We have other terms as well. So in order to evaluate this, so this is the when you simplify all these brackets, then you will get the first term as an times h times n times x raised to n minus 1 etc. Okay, now in order by using the induction hypothesis, we can say that delta n minus 1, that is the n minus 1, the difference of a polynomial of degree n minus 1. So we have already assumed that this will be the coefficient of x raised to n minus 1. So this is the induction hypothesis, coefficient of x raised to n minus 1, that is an times h times n into n minus 1 factorial, and h raised to n minus 1. So this becomes when you consider all these, you can write an times n into n minus 1 factorial is n factorial, and h times h raised to n minus 1 is h raised to n. So this is nothing but coefficient of our the leading coefficient of x raised to n in f of x, coefficient of x raised to n times this is n factorial times h raised to n. So this proves p of n is true. When you evaluate delta raised to n f of x, that will be this one. Okay, so from this you can say that p of n is true. Okay, so this proves the fourth property of this forward difference. Okay, and the exercise of this section 22.1, there are some particular functions are discussed. For example, I will put one example here. This is our example. If you take f of x equal to some sin x, then you can easily write if the interval of differencing is h, then how to find delta f of x. That is, delta f of x is equal to sin x plus h minus sin x. Okay, so this is what called the first forward difference. So using this, the sin c minus sin d formula, you can simplify this. We know that sin c minus sin d is equal to 2 cos c plus d by 2 sin c minus d by 2. So we write this is 2 times cos c plus d by 2, that is this plus this by 2, that is 2x plus h by 2, and we have the other term sin c minus d by 2. So this is c and this is d. C minus d will be h, and that will be h by 2. So this is the first forward difference of the function f of x. In the similar fashion, there are a number of examples are discussed in the exercise. So please go through it, and if there is any doubt, please come out with the doubts, we can discuss.